Yes, I will today talk about, as mentioned, test particle motion in a regular black hole spacetime. And this is joint work with Alberto Garcia, Jutta Kunz, Klaus Lemmerzahl, and Alfredo Macias. And this is the outline. I will first tell you something about the spacetime that we consider here, then about test particle motion with an emphasis on circular orbits, and a little bit about charged particle motion, but there's more work to do here. And then I will go on with our analytical work for time-like orbits in the space-time for neutral test particles, and a bit about the Periastron shift and a summary. So first, the space-time. As you all know, most of the black hole solutions in general relativity possess a singularity at its center. And the physical nature of this singularity is quite unclear. We don't really have to know what to do about it. And this is also the reason why Penrose came up with the cosmic censorship conjecture, which is still not proven, which says that such singularities should be hidden behind a kind of screen which prevents that some outer observers can get information about the singularity directly. And to tackle this problem, Bardeen introduced some regular model which does not have, did not have such a singularity. And this was, so to say, an onset for this study of regular models. And many other authors also developed quite of, let's say, zoo of regular models in GR. And but in contrast to that, the first regular solution of the Einstein equations with a physically reasonable source was found by Ayon Beato and Garcia in 1998. And they found it as a solution to the Einstein equation coupled to a nonlinear electrodynamics. So what is here modified is not the gravity, but the electrodynamics. So it's a charged solution, two-parameter, mass and charge. And this solution does not have a curvature singularity at its center. It's completely regular there. And by the way, later these two guys also found a physical reasonable source for the regular model, which was originally proposed by Bardeen, I think, in 2000. Yes, and the question that I will talk about in this in the next half an hour or so is what are the trajectories of massive test particles in this space-time, and how do they differ from geodesics in other known solutions, singular solutions, in particular for the Schwarzschild and the Rising-Nordström solution. As I said, the space-time is an exact solution of the Einstein equation coupled to a nonlinear electrodynamic, and does not have a curvature singularity. And the nonlinear electrodynamic is given by a Lagrangian, nonlinear Lagrangian, which depend only on the electromagnetic field strength. And this Lagrangian fulfills the weak energy condition, and if you go to the weak field, then you will recover Maxwell. And the metric can be written in this way, so it's spherically symmetric. You have GTT is 1 over GRR, and given by this expression here. Here M is the mass of the black hole, and Q is the charge in this nonlinear electrodynamic. And the electric field you get out of your Lagrangian has then just a radial component, as it should be for spherical symmetry, and looks like this here. So what characteristic does the space-time have? If we set the charge to 0, then we will recover the Schwarzschild space-time, which is very nice. What is not so nice is that if we increase our charge beyond the limit of 2m, then the energy density of electric field does become negative in some interval for the radius, some small interval. And this we consider as really non-physical, and so we will not talk about this any further. So asymptotically, as you let go the radius to infinity, you will recover the Rising-Nordström solution. So this is also very nice. if you go far away from the black hole, then you have what you know already from singular solutions. So if you go to r equals 0, so to the center where usually the singularity is located, you have a kind of de Sitter behavior in the sense that the GRR component looks like in de Sitter space where the cosmological constant, so to say, is given as a function of the charge. And here you also see for if the charge is smaller than 2, then this will be positive. In the space-time, you may also have horizons. So at the point where GTT are equal to 0, you have horizons, and this is given by exactly the solutions of this polynomial equations. And it turns out that if your charge is small, namely smaller than this value here, then you will have 2 horizons, as in the Reisen-Nordström case. If you have this critical value, then you will have 1 horizon, and if you further increase your charge, you will have no horizon at all. You can see this also here. This is GTT as a function of r, and you see this red line below here. This is the Schwarzschild case where you have the horizon at 2m. And then you increase the charge, and you see that you have, for small values, you have 2 horizons here and here. And if you further increase the charge, then you will eventually reach this critical value here, where you have only 1 horizon. And if you further increase it, then you will not have any horizon at all. But notice that if you have no horizons, this is not a problem here, because you have no singularity at the center. So you will not have a naked singularity, because simply there is no singularity. Okay, let's come to the equations of motions. This is just the usual geodesic equation with this electromagnetic part. And here, so capital Q is the charge of the central object, and small q is the charge of the test particle, and S is the proper time here. Let me note that in this space-time, due to the nonlinear electrodynamic, null geodesics do not describe the orbits of photons because they interact differently with the nonlinear electrodynamics. So what you have to do here to really look at light propagation is to derive an effective metric for these photons, which was done by Novello and collaborators, I think in 2002. So what we do here is we consider massive test particles and we normalize them according to this here. So with this electrostatic potential here, which is derived from the electric field, you get these 2 constants of motions as usual for spherical symmetry, the energy and the angular momentum. And with these 2 constants of motions, and with the spherical symmetry, you can of course restrict to the equatorial plane. And with this normalization condition, you can decouple the geodesic equation and get this ordinary differential equation for r over s, or dr over ds. You see, I call this capital R with index q for the charge of the test particle. And I will first tell you now about the case where we have really a test particle, so without charge. Again, this is the equation of motion written in its outwritten, so to say. And as you noticed here, we have only q squared, l squared, e squared, so we may choose all of them greater than 0. And for geodesic motion to be possible, we must have, due to the square here, that this polynomial or this function here is greater or equal to 0. Note here that this is always possible if the charge is small, so if we have 2 horizons. But if we increase the charge beyond the critical value, where we have no horizon, then there exist values for the angular momentum and the charge and the energy such that geodesic motion is not possible. So note that for r equal to 0, we saw that the Young-Beato-Garcia metric differs significantly from the usual singular solutions, from Schwarzschild and Reisen-Nordström or Kerr or whatever, because of this de Sitter behavior at the center. So it can be expected that in a more stable circular orbit will also be modified according to this feature. And as we just saw that the charge, if the charge is large, there may be regions where geodesic motion is not possible. It could also happen that some kind of gaps appear where motion is not possible, and in particular where stable circular motion is not possible. So to derive the equation which determines circular orbit, we just did a simple substitution to get a polynomial here on the right-hand side. And then we have just the condition that the polynomial should be 0 and its derivatives should be 0 at the same time. So if you solve these two equations for E squared and L squared, you get these two expressions here, where A is also a polynomial in U. And from the first equation here, you see that for a circular orbit to exist, it is absolutely necessary that this function A here must be larger than 0, because else the energy would become imaginary or complex. And if we now substitute this polynomial here as B of U, then we see from this condition, and that this here must also be positive, that also the second polynomial must be greater than 0 or equal to 0. So if you analyze now these two or these conditions for the existence of circular orbit, you get something very similar we just saw on the talk before for the Kiak-Ziel-Sepsos black hole. I don't remember what is the right pronunciation for this Opava-Lifshitz. Thank you. First you see here circular orbits. Okay, here you see the radius of circular orbits versus the charge of the space-time. Here, this dashed black line is the outer horizon. And then you see in this light gray region here, you may have circular orbits. In the right regions, you may have no circular orbits. And you already see that this is quite similar if you imagine it to be turned around. The axis, it looks just like what we saw in the talk before. So especially you have here this gap where you have no circular orbits at all. But now we want also to consider stable circular orbit. So as an additional condition, we need that the second derivative of our polynomial, our function, is smaller than 0. And if we consider this too, then we get this picture here, where now in the dark gray regions you have stable circular orbits. The light gray region is unstable circular orbits, and white region, as before, no circular orbits at all. And you see now here that you have this really similar structure. Yeah? You have beyond the critical value, which would correspond in Reisen-Nordström, so to say, to naked singularities. You have a region of stable circular orbits. Then you have a region where you have no circular motion at all. Then a region of unstable circular orbits, and then again stable. This is up to this point here, which is approximately 0.7. If you further increase, then you will get eventually to the point where this white region here disappears, and you only have stable, unstable, stable again, which is up to approximately 0.75, which is the point where this extremal value here appears, from which on you only have one region of stable orbits again. Sorry. So let us compare this situation to the Reisen-Nordström case. If you look at this, you have again here the radius of the stable circle, the innermost stable circular orbit against the charge. So if you look at this, at first glance, it seems to be very similar. But note two things. First, the scaling here for the Eon-Beato-Garcia spacetime, the critical value of the charge is about 0.63, and resonance limit is 1. So, and then if you go to extreme case, you see that in this spacetime here, the innermost stable circular orbit is at about 4.4 m, and in resonance limit just exactly 4. So you see some subtle differences here, but be careful with this because you're really comparing two different spacetimes. This is always a bit difficult to really judge here the differences. Okay, let's now turn to the case of general time-like orbits. And we still here have the condition that the right-hand side of our equation of motion has to be positive for geodesic motion to be possible. And if we take now a closer look on this function here, then we see that if we want to go to infinity, then we have to have the energy must be large enough for this to be possible. And if you want to go to hit the center, so to say, then you see that this is only possible if you have angular momentum 0, so if you have radially infalling particles and the energy also large enough. You see if L is equal to 0, this cancels and this cancels, you just have what you have here. So as we need to know the regions where this function here is larger than 0, we take, of course, a look at the points where it is equal to 0, and this gives us the boundaries of this region where we may have geodesic motion. And so if we know how this function behaves at its endpoint, so at r equal to 0 and r equal to infinity, and know all the positions of the 0, we know exactly how this looks like. So the type of geodesic motion changes if the number of zeros changes if we adjust the parameters, so to say. And the number of positive zeros changes exactly at double zeros, which correspond to circular orbits again. So you see that the analysis of circular orbits really gives you already the complete structure of general orbits in time-like orbits in this space-time, or in any space-time actually. So and this now looks like this. Let us first for comparison set the charge to 0, so this is Schwarzschild space-time. We have here the angular momentum squared over the energy squared, and you see here the red solid lines corresponds to combinations of E and L where you will have a circular orbit. And these are now the boundaries of the regions where you have different kinds of geodesic motions. So for example, in this small region here, this corresponds to the case of, so to say, planetary orbit, bound orbits, and orbits which fall into the singularity. This is indexed by the star here. And so you can go through all these 4 regions here and see the different combinations of time-like orbits which are possible. This is just the usual Schwarzschild case, to remind you. And if we go now up with the charge, then you see that not so much happens, just the red lines are shifted a bit. So the general structure of time-like motion is really similar to Schwarzschild and also to Reisner-Nordström space-time. You do not see conceptually difference here. So this is still for the case where you have 2 horizons. If you now further increase the charge and come to the case where you have no horizons, this looks a bit different. What happens now is that here appears this new region of stable circular orbits with the endpoint at L equal to 0, which is again the same as in the talk before. So this inner region of stable circular orbits really corresponds at its inner edge to particles which are not, let's say, circular in the common sense, but just particles which sits there and does not move any more. So you see they don't have any angular motion, and of course they don't have any radial motion, so they're just like freezed, so to say. And also at the other edge of the inner region, L goes to infinity, the angular momentum, just as it was before in the talk. And then here is still what we saw before. Here you have your stable circular orbits up to a certain radius and combination of E and L, and then unstable orbits again. So this is now the case where you have an inner region of stable circular orbits, then a region where you have no circular orbits at all, remember, white region, and then, So this is the case where you have here the stable regions, then no circular orbits, then unstable circular orbits, and stable again. Next we will see the region which is between these 2 points, so where you have stable, unstable, stable again. Oh, I'm sorry, I'm going in the wrong direction. So if you further increase the charge, then you will see eventually that these two lines will join at some point up here, and so you will have stable orbits, unstable orbits, stable again. And if you increase it further, you can see it here better. So this is now the case where you have inner stable, unstable, and then stable again. Okay, and still you have the case that the inner edge is, so to say, frozen. By the way, note that this situation is not too different from the case that an observer at infinity, which looks at a particle approaching an event horizon, will see that the particle freezes in his own coordinate time. He will never see that the particle crosses the horizon. Here it is similar but still different, because the particle also in its own proper time is frozen and does not move anymore. Okay, if you further increase, then eventually this small region of unstable orbits will vanish, and you will get a picture like this. Okay, so let's go to charged particle motion. So here we have a slightly modified equation of motion due to the charge of the particle we are considering here. Sorry. Still, due to the symmetries, we may choose that the angular momentum is positive. We may choose that the charge of the black hole or the central object is positive, and then we may choose either the charge of the particle as we like or E as we like. It doesn't matter. We have just to decide on the signs of these two objects. So if we consider now general time-like motion, then we have for the behavior at infinity a slightly modified behavior. So we not have still this E energy equal to 1 plus minus 1, but it's modified by a small q over a capital Q proportional to this. And if we go to 0, we have but again that we need a radial motion for this to reach the origin. And although it does not look so much more difficult than the case where we have particles without any charge, the discussion here is really complicated, and for a start we restricted ourselves to the case where we have horizons and to the case where the charge of the test particle does not become too large. Actually, this is kind of phenomenological chosen, so we don't really know if this. I think we can go a bit further here, but with our method, but we will see. Okay, so just some first results here. Here you see the radius of the innermost stable circular orbit against the charge of the central object. Here again the outer horizon. And now you see here in the middle what we saw before, the ISCO for neutral test particles, And if you switch now on a charge for the particle, you can go a bit up or down here according to the sign of your charge of the particle. So this further modifies the innermost stable circular orbit, of course, as is also the case for Reisner-Strömung, for example. On the right-hand side, you see here a diagram for general time-like orbits. Again, angular momentum squared over the energy. I'm sorry. Okay, this one here is for oppositely charged test particles, and this here for test particles of the same charge. And you see that this is qualitatively not so different. You see that, of course, ISCO is somehow located at different position, but because the charge here is still small, as we assumed from the very beginning, the modification is also not too strong. Okay, I will now go on with the analytical work we did for neutral test particles, so without charge. And we considered general time-like motions and derived the analytical solution for the equations of motions. Sorry. So, as I said before, with this kind of substitution, we can significantly simplify the equation of motion, which is somehow similar to the usual 1/r substitution for Schwarzschild, for example. And you see the resulting equation of motion looks like this, where P6 is just a polynomial of degree 6. You can reformulate this now in terms of an integral equation in this way, and you want to solve this for u of phi. And to do this, you can first notice that this kind of integral here is the genus 2 hyperelliptic integral of the third kind. I will explain you a bit what this means. So some of you might be familiar with elliptic integrals. This you will have if this factor here vanishes, and you will have here a polynomial of degree 3 or 4. If you add a factor here in front, you go from first kind to third kind, if it does not coincide with zeros of this polynomial. And genus 2 just means that you have a polynomial of degree 5 or 6 here, which is here the case. And we considered before this kind of problem for the equation of motion in Schwarzschild-de Sitter spacetime. And if this factor here would not be present, we would perfectly well know how to derive the solution. And to make use of this knowledge here for the first kind integrals, so for if this factor would not be present, we split this problem just in two parts by introducing a new affine parameter, lambda, which is given by this equation here. And you can think of this parameter as a kind of analog to the Mino time, if you are familiar with it. This parameter was introduced to completely decouple the equation of motion in Kerr spacetime by Mino in 2003. So if you introduce such a parameter, you can split this in two parts, where you have here the usual first kind problem, where we know the solution and which is completely analogous to the equation of motion in Schwarzschild-de Sitter spacetime. And then you can solve this here subsequently, which becomes then easier to do. So let me tell you a bit about the mass here. What you need as basic function is the Riemannian theta functions, and this is you have a series over exponentials. You have a lot of parameters here, most notably the Riemannian matrix tau, which is symmetric and by definition symmetric, and its imaginary part is positive definite. And by the way, this is also the basic function which you can use to introduce the Jacobian elliptic function, or also the Weierstrass elliptic functions. which are then given as fractions of these theta functions with different numbers here. And we do here basically the same. So we define a sigma function, which is just the shifted theta functions with some more parameters listed down here. You don't need to really follow this. And then the remaining problem here is just that this theta function here, in our case, is a function of an argument z, and this argument z is an element of the complex number squared. So it's a vector with two components. And of course, we want to find the solution for some radius with just one real quantity, and we need to somehow come back from this complicated object at the complex number squared to the real radius that we want to compute. And this is done by considering the manifold on which the sigma function vanishes, because this is a one-dimensional submanifold of the complex number squared. And if you do this and then first transform your equation in some standard form with a polynomial of degree 5 here, this can always be done for polynomials of degree 6, then you can find the solution to this equation in terms of sigma function, again as fractions, basically as fractions of different theta functions, as is in the elliptic case. And what you need to do then is you have your parameter lambda with some constants, and the other, the second component of your vector, you find from the condition that this must be satisfied. And if you do all this, then you will arrive at this equation here for your radius r of lambda. See here the derivatives of the sigma functions and this charge again. Okay, and as I said, you then can derive the solution for phi. This looks very complicated, and I just want to show you how it looks like. You don't need to go into the details here. You have many different components here, but I just wanted to show to you that you can really do it. And it's it looks very complicated, but as it always is, if you know how to do it, it's not so complicated anymore. Okay, and using this analytical solution, we then really plotted some orbits, and this really works quite nice. Okay, so the last part is about the Periastron shift, which is, so I go back here, just the difference between the point here, which is farthest away from the center, and after one revolution, the point when the particle is again farthest away from the center. So remember the equation of motion for r of phi. So we have here the function that we dealt with the whole talk, modified with the angular momentum because we consider it as a function of phi. And now the Periastron shift is just the difference between 2 pi and the period of our radial equation. So if your periastron is again encountered after an angle of 2 omega r, then the Periastron shift is defined as the difference between this angle and 2 pi. So just like, so to say, the difference from this general relativistic orbit from the usual Keplerian orbit, where this of course would be 0. And here again, you get this kind of integral where you have again this connection to elliptic or hyperelliptic functions. So as you saw, the solutions for r is quite complicated, and to see something here, we decided to expand these expressions in powers of the charge. So we consider here the limit of small charges. And we fixed the peri and the apastron, so the extremal points of the bound orbit, and we consider energy and angular momentum as functions of q. And if you do this, then you will arrive at an expression for your shift, which is, so to say, the usual Schwarzschild expression minus 2 pi plus the correction due to your charge squared of course, Q appeared only squared, so you will have no linear correction. And we will neglect any further terms. So if you substitute now at usual the semilattice rectum and the eccentricity in this way, then you get first the usual Schwarzschild term, which is just given here. Here, capital K of small k is the complete elliptic integral of the first kind. K is given here. And then you see that the correction due to Q squared becomes already quite complicated. You have here again these elliptic functions which with some factors in the front, and also complete elliptic functions of the second kind with more or less complicated factors in the front. So if you now do here an additional post-Newtonian expansion, so for the weak field, you will get, as expected, because in the weak field the Beato-Garcia spacetime asymptotically approach the Reisner-Nordström spacetime, you will get exactly the same result as you do if you do this for a Reisner-Nordström spacetime. So to decide if you looking at an object which creates an Beato-Garcia spacetime or a Reisner-Nordström spacetime, you really have to go to the strong field. In the weak field, you will not see anything. Okay, let me summarize. The Beato-Garcia spacetime is a charged regular solution without any curvature singularity. It asymptotically approaches Reisner-Nordström, and it reduces to Schwarzschild if you set the charge to 0. In the strong field, it differs significantly from the Reisner-Nordström spacetime, as due to the de Sitter-like behavior at its center. And due to this, also the innermost stable circular orbit may not come as close to the horizon as it does in Reisner-Nordström spacetime, if you look at least at the extreme case. So we also did an analysis of general time-like motion, and we saw that this is quite similar to the Reisner-Nordström case, as long as you stay in the physically reasonable interval of charge smaller than 2. And as I learned today, also similar to the symmetric KS solution in modified Horava-Lifshitz gravity. So we also had a look of the modification of the ISCO due to a charge of the test particle. And we also considered general orbits, all for the case that the charge of the particle is not too large. And we derived the analytical solution for the equation of motions for neutral test particles, and considered also the Periastron shift, which in the weak field does again look exactly the same as Reisner-Nordström. And we do also want to continue our research here. And first of all, which is quite obvious, it would be nice to consider particles with arbitrary charges, so also large charges. And also consider for this case the analytical solution and the Periastron shift. And as another connection to the talk before, and I think also to the following talk, if you consider this equation of motion for charged particle, the structure of this equation is very similar to the equation of motion in the spacetime, in this Horava-Lifshitz modified gravity spacetime. We tried to find analytic solutions here for quite a while now, but this turns out to be very complicated because you have several issues with quartic curves which cover elliptic curves and so on. This is a really complicated issue, and we made some progress, but it will take really much more time, I think. So, and more on the long-range perspective, so to say, it would of course be very nice to consider a rotating version of the spacetime. But as at least I am not available of any progress in that direction, so I don't think that there are any rotating regular black holes which are in this nonlinear electrodynamics regime. And as an additional point, it would also be interesting to somehow figure out how special really the nonlinear Lagrangian is that Aaron, Behat, and Garcia choose to derive their solution. So how much can we generalize this kind of Lagrangian and still have the same structure of stable and unstable circular motion? Yeah, that's all. Thank you.